Hello, I'm Laura Lynn McDaniel, your session moderator. Welcome to this session focused on prototyping and development. We'll have two quick case studies in this speed round, one from aerospace and one from energy. And then we'll take your questions. During the presentations, please use the chat function to enter your questions, and we'll get to as many of them as possible at the end of the presentations. And with that, I'd like to introduce your first speaker, Owen Timlin, who's from the Technology House. Owen's going to share the story of a 3D printed propulsion system on NASA's Seeker robotic satellite. Owen, session is yours.
Awesome. Thank you, Laura Lynn. Today I'm going to be talking about a project that we worked on with NASA Johnson on their Seeker robot. And we utilized the Carbon 3D technology. Obviously, this is much more of a condensed presentation, just to fit the 5 minutes. So if anybody has any questions after, I'm more than happy to answer those or, go into a little bit more detail. But just to get started, so the Seeker program is a NASA free flyer technology demonstration project for autonomous robotic inspection. So Seeker, as you can see in this slide, is the little cube satellite here on the bottom right. And so that is responsible for inspecting the Cygnus cargo spacecraft. So the Seeker is approximately the size of a loaf of bread. So what NASA wanted to do was they wanted to rapidly and cost effectively produce 4 high performance thrusters for the cold gas propulsion system with the new Seeker robotic free flyer inspector. So that's just a little bit of a background on Seeker. So the challenges that they were facing was there was a lot of uncertainty in developing an effective cold gas thruster system in a highly constrained volume that could integrate several critical components. So it needed to have 4 separate cold gas jets, gas tubing and fittings, integrated bracketing to hold the assembly, and design accommodation for all other sensors in the proximity. So they had exactly 1 year from project kickoff to launch. So working on an extremely condensed timeline to get this Seeker program up into space. So traditionally, they would rely on more traditional processes such as CNC or other metal forming processes. But due to the time constraints and the need to move quickly and iterate rapidly, they were kind of looking for different solutions. So they came to us to see if we had any ideas for how they could create specifically this manifold that would go into the Seeker robot to help with the cold gas thruster systems. So what they needed was 1, a lightweight material. 2, there's extremely small throat dimensions on this part. It's approximately the size of a lead mechanical pencil. And just to show you how thin that is, I brought a mechanical pencil lead just to show you how thin that throat dimension is that they needed on this part, not to mention the internal passageways that go through this part. And then also the material needed to be temperature resistant. So it needed to be able to live up to what it would see up in space. So the solution that we came up with working, hand in hand with NASA Johnson and Carbon was we thought, okay, well, this would be a perfect component for additive manufacturing. We have a lot of technologies in-house, so we were kind of seeing which one would be the best process-wise and material-wise, and really we came to the conclusion that the carbon process would be the best for creating, the really small, intricate features, and Carbon CE 221 proved to be the perfect material for the requirements of this mission and the part being validated for space. So prior to Seeker, there was no 3D printed pressurized plastic component that had been certified by NASA for ground or flight use around operators. So because of that, the Seeker team had to go out on an extensive development and qualification test schedule to understand the capability of the components and test methods to screen for process variations. So as part of this development program, the team pressurized over 100 articles to failure, improving structural design and sealing interface interfaces. Within that 1 year from initial project idea to launch, TTH and NASA had over 10 design iterations. So that's moving extremely quick. So we would print, send to NASA, they'd test, they'd iterate, print, send to NASA, test, iterate. And that's how it went, for over 10 plus cycles. So once the design was locked, obviously we needed to ensure NASA that we could build this repeatedly. So we had to essentially achieve 0% scrap to meet NASA's stringent testing and production requirements, which we did. And in April 17th, 2019, the Seeker launched into space. So it was a very successful project for Technology House, for NASA, and it was a great way to showcase Carbon's process and materials. Thank you very much.
Thank you, Owen. And now we'll go to our next case study from Enrique Enriquez, who is the president of KW Micropower. He'll share with us how 3D printing created cooling channels equals more power. Enrique, session is yours.
Hi, my name is Enrique Enriquez. I am the president of KW Micropower. We're a designer and manufacturer of high-density generators. We try to put most amount of energy into a small compartment as we can. And today I'm here to tell you a little bit about our experiences with additive manufacturing. Little background, prior to KW Micropower, I spent a career working in aerospace. As a matter of fact, I worked on some of the early space satellites back in the early 80s. So I've been very fortunate of seeing the whole engineering progression from the early days of CAD CAM to where we are today. As a matter of another thing that we did is we bought one of the earliest machines. I was fastest. I think it was number 2. So that can give you an idea how far back we go into 3D printing. In designing our microturbine, I ran into a problem. There was this part that you're seeing here on the screen that has very complex channels. And there was absolutely no way of getting this part made with conventional manufacturing methods. I was working also with the high-end additive manufacturing shop in New York, and they were not also able to make this part. So as a last resort, I went to the IMTS show in 2018, and I was looking for a miracle, somebody who could build our part. And I ran into a friend of mine that was doing consulting for another firm at the time, and he's extremely a wealth of information. So I told him about my problem, and he told me, you need to see Velo 3D. If anybody can do it, they can. So I went over to their booth. I met Benny Bueller, the company founder and CEO, and Benny put me in contact with their top people. And I showed him my problem, told him the difficulties I was having getting those parts, components made, and they decided to give it a shot. A month later, they come back, and not only have they figured out a way of doing this part, but they already knocked off 33% of the weight. So that was just an amazing experience with Velo. So ever since, I've been a huge fan of their technologies and their capabilities. A following project, we did an igniter system in Hastelloy that we had combined 3 very difficult parts into one. And at the end, we had reduced about 33% of the cost in manufacturing this part into one component. So that was project number 2 with Velo. Number 3, they introduced me to a company called Topology, which is a high-end software house with amazing capabilities. And so working with those 2 was just a dream. So the next task was to take a part of our microturbine that houses a generator. And this is an aluminum part, roughly about 10 inches long. 7 inches in diameter, and we wanted to see if we can do something more than just reduce the weight on this part. And I had done some previous experiments with putting cooling channels within the part and have been very successful. So turned it over to a topology, and they were able to carve out 44% of the weight. And in addition, we came up with a scheme to flow fuel through the part, which in essence took the heat of the generator and passed it on to the fuel. So we had twice the gain, reducing the weight of the part 44%. But in addition, we able to put energy into the fuel, which is going to make our system that much more efficient. So those are the type of results that I've been getting with Velo. I mean, by the time that we are done with our flight portion of our generator, which is we generally use as an auxiliary power unit, uh, we should have a very, very light unit that not only it can do additional things that we were not able to do before. So basically, 3D printing gives you a tremendous amount of freedom to be able to go out there and do things like you've never done before. As an engineer, I call this the renaissance of engineering, because the engineering is coming up with these new capabilities are going to be able to do designs that are way beyond our imagination at this point. So at KW, we maximize 3D printing, and again, for weight reductions and additional functionality, it's just nothing else that available that you can do as much. So I'm just so excited to be a part of this revolution in manufacturing. So that being said, I'm open for questions, and that's all I have today. Thank you.
Thank you, Enrique. And now we'll go to the audience questions.